So we left off on the on this slide. I had some issue with the audio, so I just want to make sure that we cover that, that we get this slide covered. So the two basic vector operations are scalar multiplication and vector addition. In operations with vectors, numbers are usually referred to as scalars. So for example, here the number 2, we're going to consider that a scalar. And so when we do a scalar multiplication with vectors, we will just distribute that scalar times the vector. And for example, if we have 2 times vector v, this vector 2v is going to be the absolute value of 2, which is 2, times as long as vector v. And the one that I was going to go over was if we have the scalar -2 and we multiply that times the vector v. So this vector here is still 2 times as big because the absolute value of -2 is +2. So it will be 2 times as big, as long as vector v, just like that one. The difference between -2 for the scalar and +2 for the scalar is going to be the direction, but they will have the same length, and it will be 2 times the length of the original vector, vector v. When k is positive, k is the scalar, remember, it represents a number, a real number. K times v has the same direction as vector v. So if, for example, we have here the original vector, which we'll call it v, and we have here a scalar times the vector. And so if that scalar happens to be positive, it's not going to change the direction. As you could see, for example, here, +2 times v is 2 times as long, but it is in the same direction. Now, if k is negative, then the product of kv, if the scalar was to be negative, then that vector kv will have the opposite direction of the original vector, as we could see here. So for example, let's look at this one. -3/2 times v is negative, so the direction changes to the opposite direction of this original vector. Also, -v is the same as having the scalar of -1 times the vector, and so because of that, we're going in the opposite direction of this original vector. And then you could also see how for the other vector, which is v, I'm sorry, 1/2 times v, that one is half the size of the original vector, and you could see that here. To add two vectors, let's call them u and v, geometrically, first position them without changing their lengths or directions, so that the initial point of the second vector, in this case will be, this is the second vector, so the initial point of that second vector coincides with the terminal point of the first vector. Here the first vector will be u. So if we were trying to find u plus v. Now here we have the geometrical representation. So we have vector u times vector v, and so we take the initial point of the second vector, like we explained on the previous slide. So the initial point is here. And then we want it to coincide with the terminal point of the first vector, which will be that one there. So if I was to match, to make those 2 points match, I'm going to try to do something here. So it will be like if I was shifting. Oh, I cannot do that. Yeah, no, I am not able to. Maybe with the mouse. If I was to move this one, so remember what I am trying to match is this point, the one in pink that I circle in pink. So I'm going to circle it here as well. And so that is the point. I'm going to see if I can move this whole thing. Maybe. Okay, so it's not working. Okay, so this is what I was trying to do. So, oh no, it's not gonna work now. I think that one. So imagine this is vector V. I know it's a little longer, but if we try to move that, and I'm trying to position the terminal side, I'm sorry, the initial side of that vector, so that it overlaps with the terminal side of the first vector. And so if I continue to move it, so it will look like that. And that is actually what you could see here on this side of the, what you could see here on the right side. So here we have, originally we had, that was vector u, and then we had the other vector that we shifted up. And we actually call this the parallelogram rule. And so what happens after is if we connect the initial point of vector u, which will be there, with the terminal side of vector v, then that line is what will give us the addition. So it will be like the initial point of u, and then draw a vector that stops here at the terminal side of vector v, and that will be our addition u plus v. And we call it the parallelogram rule because you could see that if you trace that, you do have a parallelogram. Now that will be the geometrical representation. However, the arithmetic or the arithmetical representation is a lot easier. All we're going to do is add the horizontal components and add the vertical components, just like if we were adding x plus x and y plus y. However, remember the way that vectors are defined. So if the name of the vector is u, the horizontal component is going to be u1. And if the vector is v, the horizontal component is going to be called v sub 1. So here we have the addition of the horizontal components. And then u sub 2 is representing the vertical component, v sub 2 is representing the vertical component. So it's very simple to add two vectors. It's just good to know what the geometrical representation will look like. especially for word problems and if you have to take physics. That will be a very good skill to have. Now, next operation is called the scalar multiplication. So remember, k is just a real number here, and the vector is called u. And so the scalar times the vector, we will distribute the scalar times the horizontal component and times the vertical component. And then here, that will be our new vector. So it's also very simple, just like distributing a constant times the elements of a parenthesis inside a parentheses, or the terms inside a parentheses, or when you did scalar multiplication with matrices, same thing, you used to distribute the scalar times every single element inside the matrix. So if we have an original vector called v, and then we have another vector with the opposite sign of the vector, of course, you know it's going to have the opposite direction. And also that -1 will be like the constant k that we were talking about. So for it to be negative, it's changing the direction of the first vector. And we will again distribute the -1 to the horizontal component and also to the vertical component. Also, we have the difference of two vectors. It is defined as the addition of one vector times the opposite of the second vector, as you can see here. So if you want to think of adding negative numbers or just subtracting numbers in general, that's what we're going to do. So if you're getting the difference between the vectors u and v, you will still subtract, in this case, because it's the difference, the horizontal components, and also subtract the vertical components. You can see here the representation. So let's see. The original vectors will be u is there, and then we have vector v, which is here. Okay, so if you look at the one on the top is -v, so that will be going in the opposite direction. However, it has the same length as the one in yellow. And if we add or subtract the two vectors, subtract vector v from u is the same as adding the opposite of vector v. So it will be like we're adding this vector here that was in blue. Well, you could still see it. So if we add that to vector v, which is the one in green, then we will be adding u plus -v, which is here. So if we have those 2 points connecting to each other, then we will get the result, which will be here. To represent u minus v geometrically, you can use directed line segments with the same initial point. The difference u minus v is the vector from the terminal point of v. So we have that here, the terminal point of v, to the terminal point of u, which is here. And so that will be our difference of the two vectors. The difference u minus v is the vector from the terminal point of v to the terminal point of u, which is equal to u plus -v, as shown in the figure from the previous slide. The component definitions of vector addition and scalar multiplication are illustrated in example 3, which we're going to get to. And in this example, you will notice that each vector each of the vector operations can be interpreted geometrically, as we were trying to show you earlier. So we have two vectors here, vector v and w. So for our first problem, we're going to be distributing the scalar times the vector. So it's going to be -2 times, well, let's write it down first. And so remember, we must distribute to the horizontal and vertical components. So the resultant vector will be -4, 10. Okay, so next for w minus v, we could consider the horizontal components. And since we are subtracting, I'm going to go ahead and put a minus there, but of course you could, and in fact, this will be wrong. Let's just do this. So it will be w, the horizontal component of w is 3. So it's going to be 3 minus the horizontal component of vector v is -2. But we have a minus already in there, so I'm going to go ahead and use parentheses. Close the parentheses, and that will be only for our horizontal components. Now, for the vertical components, vertical component of vector w is +4. And then the vertical component of v is 5, so it will be 4 minus 5. And then we'll do that. So we will have 3. We have to clear the negative sign here, so that will be a +2, comma, and then still 4 minus 5. So 3 plus 2 is 5, and then 4 minus 5 is -1. Now, for the next problem, we're going to have vector v added to 2 times w. So I'm going to just go ahead and write down what vector v will be from the original question, -2, 5, the one here. And then we will be adding 2 times vector w, which is 3, 4. So here we will have -2, 5 plus, now I'm going to go ahead and distribute the scalar. Remember, that's scalar multiplication, so this will be 6, 8. And now from here, what I can do is combine the horizontal and the vertical components. So we will have -2 plus 6, 5 plus 8 equals, and then I will have 4, 13. And that will be the solution. Vector addition and scalar multiplication share many of the properties of ordinary arithmetic. So just like you can add two numbers, like 2 plus 3 is the same as 3 plus 2, we could also do that with vectors. So it is commutative for addition of vectors. Also, it is associative, like you could say here, see here on number 2. Property number 2, you could associate or group u and v together, add those first, and then add vector w at the end. Of course, same thing, you add horizontal components and you add vertical components. Or you may choose to add first vectors v and w and then add vector u after that, and they will be exactly the same thing. So that will be the associative property. We have property number 3, if you have vectors u plus the 0 vector, it's just going to give you the same as the initial vector. And so for that, we consider the 0 vector the additive identity for vectors. Meaning that if you add a vector times the 0 vector, you get the same original vector that you started with. Now here, now property number 4, we have u plus the opposite of u. And so here, negative u is representing the additive inverse of the original vector. Now here in property number 5, we have two scalars or two constants or two real numbers multiplying to vector u. So we could multiply the scalar d times u, the components in u, and then at the end multiply by the scalar c. Or we can multiply the first two scalars and then multiply times the components of the vector. Similarly, if we have two scalars adding, but you could see how they're both multiplying to u in property number 6. And so we could distribute the scalar, for example, c times u, and then d times u, and then at the end we add them. So is associative. The properties of vector addition tells us that it's also associative for scalar multiplication. And then number 7 is almost the same, but here we're associating or grouping the vectors first, vector u and v, and then at the end we could distribute the constant after adding the two vectors, so we could do the scalar multiplication at the end, or we could distribute the scalar first to each vector, and then it will look like the one we have here, and then add them. So you do scalar multiplication first and then vector addition. So either way, you will get the same result. And then number 8, it will be the scalar 1 times a vector u, and you will get the exact same vector. And this is because 1 will be considered the multiplicative identity. And then here, we're looking at 0 as a scalar. You see how it's not as a constant. You see how it's not bolded. But if you multiply the scalar 0 times a vector, you will obtain the 0 vector, the one from here. 0 vector. And then finally we have property 9, which says that if you have a vector times a scalar, the magnitude of that vector will be the absolute value, because length will always be positive, so it will be the absolute value of that scalar times the magnitude of the vector in question. The next objective is the unit vector. In many applications of vectors, it is useful to find a unit vector that has the same direction as a given non-zero vector, meaning only non-zero vectors can have a unit vector, because remember the zero vector has no magnitude or zero magnitude. So as vector v. So to do this, you can divide the original vector, as you could see here. So the original vector will be, we'll call it v, and it is here, and we are going to divide by its magnitude. As you could see here, we're dividing by the magnitude, and so with that we will be creating, from here we will have a constant that will be multiplied to the vector, or in other words, scalar. So the unit vector u is a scalar multiple of vector v. Where is the scalar? Well, the scalar is going to be this part right here, 1 over the magnitude of vector v, the one that we want to get a unit vector from. So the vector u has a magnitude of 1 because we are multiplying by 1 over the magnitude, and the same direction as the original vector v. The vector u is called a unit vector in the direction of vector v. So let's go ahead and find the unit vector for this one. And then we will verify that the magnitude is 1 by using the distance formula. So first, what we need to find is what is the magnitude of the vector, the original first. And that is going to be the square of the horizontal component. But please notice how I am using parentheses for that. And then plus the square of the vertical component, so that will be 5 squared. So we got the square root of 4 plus the square root of 25. We add what's inside the radical first. We get 29, and we leave it like that because 29 is not a perfect square, so the square root is not an integer. And then we're going to have the unit vector, vector u, is going to be vector v, the original one that we have here in component form. And then we're going to divide that by the magnitude of vector v, which is what we found on the previous step. So we have that. Now, this part, by definition, is the same as 1 over the square root of 29 times the vector. And so if now that this is our scalar, and if we do a scalar multiplication, it will be that number times the horizontal component and also times the vertical component. So here again, for the unit vector, it will be -2 over the square root of 29 comma 5 over the square root of 29. And that is what we could call the unit vector. Now, if WebAssign does not take that answer, you know that it's probably because you need to rationalize the denominator. So it will be -2 times the square root of 29. And then on the bottom, if we have the square root of 29 times itself, of course, it's going to cancel, but I'm just going to write it down here. So this will be 5 times the square root of 29. And this is similar to having the square root of 29 times the square root of 29, which is equivalent to this expression, the square root of 29 being squared. And so if we simplify this operation, it will be -2 square root of 29 over 29. And then here, for the vertical component, it will be 5 times the square root of 29 over 29. And then that will be the vector. Now, to verify that the magnitude is equal to 1, I'm actually going to use this form of the unit vector, the one before we rationalize it. So to find the magnitude of u, like I was saying, we will use that vector, which is the same as this one, before rationalizing the denominator. So the magnitude of u will be equal to the square root of -2 over the square root of 29, and that whole fraction square. That's the horizontal component. The vertical component will be 5 over the square root of 29 and then square. And so this will be equal to the square root of 4 over 29, because you know you got to distribute the square to both numerator and denominator. So -2 squared is +4. Remember that -2 times -2 is +4, so please don't put a negative there. And then the square root of 29 squared will cancel the square root, so that's why I have 4 over 29. Now for the next fraction, this will be 5 squared, which is +25, and then we have the square root of 29 squared, so it will be 29. So from here, we will have 29 over 29, which is the square root of 1, which is equal to 1. There are two very special unit vectors, and those will be the ones with the components 1, 0, and we will refer to that vector as vector I. And not to be confused with imaginary numbers, we're just using real numbers here. So here the horizontal component is equal to 1, and the vertical component is equal to 0, as you can see here. So we also have vector j, and the component in component form is 0, 1. And so it will be the vector that has 0 for the horizontal and 1 for the vertical component. So you can see that is perfectly overlapping the y-axis, and vector I is overlapping the x-axis. And here is the note. Just remember that we are not using the italicized I, like the curvy I. We are using boldface I to indicate that it's a vector, in this case a unit vector, and the standard unit vector, and not the imaginary unit. So with the unit vectors, remember we said that vector I was 1, 0, and vector j was 0, 1. And so with that said, and also recall that this is for horizontal, the horizontal component is a 1, and here we have the vertical component is a 1. So if we put them together, then we could actually write any vector with a combination of the vectors I and j, or with a combination of the unit vectors. So over here, you could see the horizontal component of vector v is gonna come from multiplying the unit vector times whatever the horizontal component is. And then we have the here for v2, the vertical component is coming from the product here. So the scalars, which will be v1 and v2, are called the horizontal and vertical components respectively. We've been using that already. So here for the vector sum of two vectors, it's called a linear combination of the vectors I and j. And actually, no, this is not a, sorry, it's not a sum of two vectors, but it's just adding the horizontal and the vertical components. So it's a linear combination. Any vector in the plane can be written as the linear combination of the standard unit vectors I and j. And you will be able to see that with an example, but let me give you a simple one first. To illustrate the example of converting any vector into linear combination of the vectors I and j, I have chosen the vector 3, 5, so we know that the horizontal component v sub 1 is 3 and v sub 2 is a 5. So if we follow this notation here, we could see that 3 times vector I, which is 1, 0. Remember, that is the unit vector that is on the horizontal axis. And then we have vector j, which is the unit vector that is on the vertical axis. So it will be plus v sub 2, which is 5, times vector j, 0, 1. And so this will give us 3, 0, if we distribute the 3 to the 1 and to the 0. And for the other one, after distributing, we will get 0, 5. And if we add those two vectors, we will get 3, 5 which is what we had started with. The next objective is going to be to find a direction angle. So if u is a unit vector such that theta is the angle measured counterclockwise from the positive x-axis to vector u. So here we have the positive x-axis and we have vector u right here. And so the angle is the direction angle. In this case, is going to be the one in between those two segments. So angle theta will be here. So back to that slide. Then the terminal point of u lies on the unit circle, and you have u equals x for the horizontal component, y for the vertical component. And so remember how we started this course in chapter 4? We went over the unit circle, and then after that we expanded into other trigonometric ratios. So back then, if we were working with the unit circle, like the one you see on this draw on figure 6.20, is a unit circle because the radius is equal to 1. And so when that's the case, we could say that the cosine of theta, it comes from the x coordinate or the horizontal component of this vector. So that would be cosine. And then we know that y is representing the sine of theta, or vice versa. Sine of theta is representing y, or the vertical component. So we could also include the unit vectors I and j that we were discussing before. And so based on that, we will be able to find the angle theta, which we're going to call the direction angle of the vector. In this case, the name is vector u. So suppose that u is a unit vector with direction angle theta, and if v is equal to a times I plus b times j, is any vector that makes an angle theta with a positive x-axis, then it has the same direction as u, and you can write it as follows. So here we have the magnitude of v times cosine theta sine theta, because recall we're replacing here cosine. We're replacing x with cosine theta, and we're replacing y with sine theta. So here we take the magnitude out, the magnitude of v, which is here, the magnitude, and that could also be distributed. And we could do that because we're using the unit vectors I and j. And so we're going to be doing that in a minute. So because we have the vector in that form, remember a is here a number that is just multiplying the unit vector I, and b is also a number, a real number, that is multiplying vector j, the unit vectors. And so that horizontal component can also be found by calculating the cosine of theta times the magnitude of v. And this is for something that is different than the unit vector. Remember here, where would that be? For the ones here is if u is a unit vector. That was the constraint. So for this ones, we didn't really have to worry about the magnitude, because if it's a unit vector, the magnitude is a 1. So it was not necessary to distribute the magnitude. But now here, if we extend that concept, these are vectors that are not unit vectors, and so that's why we have to distribute them, the magnitude to the unit vector I and j, but also to the cosine and sine of the direction angle. Now, based on this, so vertical component, it will come from here, times the unit vector j. And just to refresh your mind, vector I is equal to 1, 0, and then vector j is at 0, 1. That is where the terminal point is, because these are in standard form unit vectors. So the initial point is the origin. So it follows the direction angle theta for V is determined from the tangent of theta, which will come from the ratio of, by the quotient identity, tangent is equal to sine over cosine of the same angle. And we already know how the sine theta is representing the vertical component, which in this case we're calling that B. And so that's why we have B here. Or you could see it here. This whole expression is representing B. And so for tangent, the quotient identity, we have sine of theta on top and then cosine theta on the bottom. So that's why B goes on top. And then here, for the horizontal component, that will be cosine, or if we have not a unit vector and we have to use a magnitude, and that is represented by A. And so that's how we will find it. Now, if we have the expression here, tangent of theta is equal to the ratio of B over A, which will be the vertical component over the horizontal component. So to find theta, that will be the tangent inverse of the ratio B over A. And we use B over A because if we look at the drawing here we have Y, but in reality, not in reality, but another way to represent that will be B. And then here for the horizontal component, that will be A. And so it makes sense that if you have a triangle, this is B and this is A and this is theta, and you want to find tangent of theta, you know you will take the opposite side, which in this case will be B, and divide it by the adjacent side, which in this case will be A. So that's another way to look at it. So we're going to find the direction angle, and I know the answer is there, but we're going to pretend like it's not. And we have this vector, it's pretty easy, as just 3i plus 3j. And remember, that's just a form to write it with the unit vectors, but another way to write it will be like this, 3, 3. And if we want to find, we could call this 3 will be A and this will be B, or from here we could say that will be A and then here we'll have B. So to find tangent of theta, we're going to substitute B with 3, A with a 3. We get a positive 1 from 3 over 3, and if we take the tangent inverse of 1, we will get pi over 4, or 45 degrees. So tangent inverse of 1. Remember how tangent is only positive in quadrants 1 and quadrants 3. However, if you find the tangent inverse of 1 on the calculator, you will get the answer in quadrant 1, which is 45 degrees, and that will happen because of the way that tangent inverse is defined. So with that said, we could also, if we were to have, let's say, negative u, it will be something like negative 3i plus negative 3j. And so from there, the magnitude will still be equal to 1, but it will have the opposite direction. So in that case, if vector u is in quadrant 1, vector negative u, or the opposite, or the additive inverse of it, will be in quadrant 3. And so the direction angle for that one, if we start on the x-axis, it will not be 45, but it will be 180 plus 45, which will be 225. I believe. But in this case, we're sticking to quadrant 1, and a very good idea is to actually plot the points. Remember that those numbers are giving you the terminal point of the vector. So if you plot 3, 3, you know for sure that you're going to be in quadrant 1. So the direction angle is 45 degrees. If WebAssign wants your answer in radians, make sure you enter pi over 4. So let's do another one here. And we're going to do the same thing. So we have that A is equal to positive 3 and B is equal to negative 4. So to find the direction angle, we're going to substitute B over A. So negative 4 over 3. And then to find theta, we will get the tangent inverse of negative 4 over 3. So if we go ahead and enter that on the calculator, so I'm going to enter tangent inverse of negative 4 divided by 3, close parentheses. It's very important that if you have a negative sign in front of your number, you use the button with the below number 3. If it's a minus, something in the middle of two terms or numbers, then you will use the minus key. But for negative, you use the one here below number 3. So if we press enter, we will get a negative answer. However, WebAssign will not take this answer. And the reason is that the way a direction angle is defined is a positive angle that goes from the positive x-axis and counterclockwise, that's why it's positive, and then the terminal side will be the actual vector. So with the calculator, we got negative 53.13. Let's round it to that. So we can see here that it could be negative 53.13. So that will be an angle. Let's give it another name, actually. So let's call that angle alpha. So that will go from here to here because it's negative in the counterclockwise direction. So that angle is equal to negative 53.13. So to find the angle that we're looking for, the direction angle, and remember it has to be positive, so we cannot use that as an answer, the one that we got from the calculator. So then what we have to do is take 360, what will be a full rotation, and then add that negative angle that we got in our answer. And I know this is just the same as subtracting that angle from 360. So this is 360 minus 53.13. And so what we will get, it will be 306.87 degrees. So remember, direction angle must be positive, and what else? Well, yeah, positive and in standard position, meaning starting from the positive x-axis and then counterclockwise, opposite as the clock, so positive angles. Okay, so for example 8, we're going to find the component form of the vector, the one that looks like this, for example. That represents the velocity of an airplane descending at a speed of 150 miles per hour. So in this case, velocity is going to be the magnitude of vector v, and that is 150 miles per hour. That will be the magnitude, and it is going at an angle 20 degrees below the horizontal. So that is very important because 20 is not actually the direction angle. And what we know is that, I'm going to zoom in here. So if this is the horizontal, it says that the airplane is going 20 degrees below the horizontal. So for the direction angle, we must start on the positive x-axis and then go all the way to the vector. So our angle here is not 20, but is in fact 180, which is a straight angle, plus 20 degrees. So that will equal to 200. So for theta, the direction angle, we will have 200 degrees. So now, following the formula that we had previously, and it will be vector v, it's equal to the magnitude of that vector times the cosine of theta times I plus the magnitude of v times sine of theta times j for the unit vectors. So I'm going to start substituting here. So we will have 150 times the cosine of the direction angle, which is here, 200 degrees. And that will be times the unit vector I, plus the magnitude of v, which is 150, times the sine of the direction angle, which is 200 degrees, and times j. So that same substitution, you could see it here. And if we were to enter this part on the calculator, we will get the number negative 140.96. And of course, times I, it's like times the vector 1, 0. From there, we will add, if we calculate this, of course, you need your calculator because 200 is not one of those common angles. So you will get negative 51.30 and times the j vector. So that is the vector 0, 1. So recall how we must distribute. So this constant times a 1. And this constant times a 0, which is just 0. So we will get negative 140.96, 0 from there. And then from the other vector, we again distribute. So that will be 0, negative 51.30. We close that. And now if we add the horizontal components, we will get that because we're just adding 0. And if we add the vertical components, 0 plus negative 51.30, we will get negative 51.30. So the final answer is the one that you see here. That is the velocity vector in component form. So to check that, because here we just assume that the velocity was giving us the magnitude. So to check that v has a magnitude of 150, like the problem said, We could check by the magnitude formula, which is the square root of the square of the horizontal component plus the square of the vertical component. And so if we could enter all of that on the calculator once, and the answer will be approximately 150, which was the magnitude of the vector, and in other words, the velocity of the airplane. So this concludes the video.